Example 8.10, warming up. The goal of this is to find a moment of inertia and apply the rotational analog of Newton's second law. So just a reminder, for point masses, the moment of inertia is sum of each mass times its distance from the axis of rotation squared. And for rigid objects, like these, it's based on the density of the object at that point times the small differential volume element. However, we're not going to actually use this equation to solve any of these. We already have them in a table, all the ones we need in a table here, so we're not going to use that integral. Newton's second law is acceleration equals sum of forces divided by the mass, and the rotational analog of Newton's second law is that the angular acceleration is equal to the sum of the torques divided by the moment of inertia. So here we have a baseball player loosening up his arm before a game tosses a 0.15 kilogram baseball using only the rotation of his forearm to accelerate the ball. The forearm has a mass of 1.5 kilograms, and the length from the elbow to the ball's center is 0.35 meters. The ball starts at rest and is released with a speed of 30 meters per second in 0.3 seconds. Part A, find the constant acceleration of the arm and ball. The constant angular acceleration, so omega equals, and for part B, calculate the moment of inertia of the system consisting of the forearm and ball, which would be I, and find the torque exerted on the system that results in that angular acceleration. Part C is T, tau. Okay. Part A, we want to find omega. So we've got delta V sub t, and we got delta t. So we could go either find omega naught comma omega final, or we could go find A, and then from either of those directions we can find alpha. So if we found A, let's go this way. Find acceleration first and then find alpha. Well, delta V sub t over delta t will be A, and then alpha is R, A equals R alpha. So yeah, we'll just say A equals R alpha there. And this one is V sub t equals R omega, and then this would be delta omega delta t. So those would be the steps. So I'm going to go this way. The delta V sub t over delta t is going to be 30 meters per second divided by 0.3 seconds, which is 100 meters per second squared. And then alpha is going to be that acceleration divided by r. So 100 divided by our radius of 0.35, that's the length of his arm, gives 286 seconds, or 286 radians per second squared. Now, to find the moment of inertia, we're going to treat the ball as a point mass. So that will be 0.15 kilograms times the 0.35 meters squared. And then for the arm itself, it's basically looks like this, a long thin rod with rotation axis not through the center, but through the end. So it'll be 1/3 times its mass times of 1.5 kilograms times 0.35 squared. So there's our mass of the ball, and here's the mass of the forearm, and notice the 1/12 in there. But don't use 1/12, use 1/3 because it was through the end, not through the center. So if you want to, you can combine the 0.35 squareds, and then it's 0.15 times 1/3 of 1.5, and you end up with a moment of inertia of 0.796 Newton meters squared. So that was A and B, and the next part we want to find the torque from alpha equals sum of torques divided by I, or the torque is I alpha, which will be the moment of inertia, 0.0796, times the radial acceleration, which is 289 radians per second squared, which came out to 23 Newton meters. Okay, exercise 8.10. A catapult with a radial arm of 4 meters long accelerates a ball of 20 kilograms through a quarter circle, which is 1/4 revolution times 2 pi radians per revolution is pi over 2 radians. The ball leaves the apparatus at 45 meters per second. So 45 meters per second. If the mass of the arm is 25 kilograms, so this is 25 kilograms, and the acceleration is constant, find A, the angular acceleration, B, the moment of inertia of the arm and ball, and C, the net torque exerted on the ball and arm. So here, let's, instead of VVAXT, I'm going to write omega alpha theta t. We've got theta is pi over 2. Omega initial is actually 0. Omega final, let's find out what that is. Omega, let's see, how's it go? R omega equals S, or equals V. And V is 45 meters per second. So omega equals V over R, which is 45 meters per second, divided by the length of the guy, which is 4 meters. So that comes out to be 11.25 radians per second. All right. So we'll plug in 11.25 there. And we can calculate alpha now from 2 alpha delta theta equals V final, omega final squared minus omega initial squared. And that will be 11.25 squared equals, okay, and then I'll divide by 2 and theta, pi over 2. We can simplify by crossing out that, and we get 40.3, and this is an alpha, so it is in radians per second squared, which lets us fill that in. Okay, the next part, we're going to take the I, moment of inertia, is going to be mass of the, what is that, a rock, a stone or something like that, times its radius squared, times 4 squared, plus the mass of the arm, which is 25 kilograms, times 1/3, and again 4 squared, because of the table, using the approximation that it is a long thin rod with rotation axis through the end. So yeah, we end up with a moment of inertia of 453 kilogram meters squared, which is what they have in the text. Good. And then finally, the sum of torques is the moment of inertia times the angular acceleration. So we just multiply these two numbers together. And to 3 significant digits, it is 18,300 Newton meters. As for the question 8.10, it asks, why do pitchers step forward when delivering the pitch, and why is the timing important? Well, my first thought is that they're adding their own forward velocity to the pitch, but it seems like that would be negligible. So, drawing a couple of really bad stick figure drawings, I'm kind of imagining that the ball starts up here and kind of goes around this direction. It might involve, could there be some kind of effect of the torque the torque around the toes? Maybe that's something that they're getting at. And they say stepping forward transfers the momentum of the pitcher's body to the ball. Without proper timing, the transfer will not take place or will have less effect. So yeah, I guess if you take his M and give him a little bit of delta V and transfer that to the little mass of the ball, and it's big delta V. I don't like to use that capital letter, it looks like volume. Alright, but V ball, then yeah, you can get quite a bit of speed out of that, a little bit of change in his momentum. I guess the timing would be right as the ball is released, his fingers are pushing forward, and his fingers are actually stopping him, are stopping his forward momentum as they put all of that momentum into the ball. That would be the ideal timing.